In the last class, you learned about logic gates. They are electronic circuits that implement Boolean algebra. Let's quickly review the three basic logic gates. First, there's the NOT gate. The NOT gate looks like a triangle with a little bubble on the output. So if we put the input as A and the output as F, F equals A naught. Well, you can write A naught two different ways. One way is to put an apostrophe after the A. The other way is to put a bar over the A. The truth table for the NOT gate has one input and one output. If the input is 0, the output is not 0, so it's a 1. If the input is a 1, the output is not 1, so it's a 0. The second gate you learned about was the AND gate. The AND gate looks like a bullet with one output and at least two inputs. Let's call the output F and the inputs A and B. The truth table also has two inputs and one output. And we want to write all the different combinations of A and B. In order to do that, it's easiest to just count in binary, from 0 to 1 to 2 and to 3. The output of the AND gate is only true if both inputs are true. That happens here in the last row, so A is true, B is true, and F is true. Everywhere else, F is not true or false. The logic equation for the AND function is A and B. You can put a dot in between the A and B or just leave them smushed together like you do in regular algebra for representing a multiplication. The third logic gate we talked about was the OR gate. The OR gate looks like a missile nose cone. It's got a rounded back and a round pointed front. So there's our output. It's got at least two inputs. We'll call those A and B for this one. And the truth table also has two inputs and one output. 0, 1, 2, 3 are all the combinations of our inputs. And in the OR gate, the output is true if either the A or the B input is true, or if they're both true. So that happens here, here, and here. And the only place that the OR gate is not true is if the A is not true and the B is not true, which happens here. The equation for the OR gate is A or B. So we use the plus sign to indicate an OR function. Now what if our logic circuit is more complicated than just a single gate? Suppose we have something that looks like this. We have an AND gate here with two inputs and an AND gate here with two inputs, and we'll put both of those into an OR gate. With an output F. And let's put a NOT gate there, and let's put a NOT gate here. We'll call this input A and this input B. Call that one A and that one B. Now of course there really is only one input A and one input B. So the B input will go here and here. The A input will go here and here. What is the logic equation of this circuit? Well, if we have an A input on this AND gate and a B NOT input, because B comes into the NOT gate and a B NOT comes out. Here we have a NOT gate with an A coming in, so an A NOT comes out, and a B comes into the AND gate here. So this AND gate has an A input and a B naught input, and we AND them together. That means we have an A and B naught output. This AND gate has an A naught and B output. The OR gate takes the input here and ORs it with the input here to give us A, B naught, or A naught, B. And that's the logic equation for this more complicated logic circuit. It turns out that this particular logic circuit is equivalent to what's called an exclusive OR gate. You may have heard of these before. The exclusive OR gate looks like a regular OR gate with an extra back on it. And it implements that logic function. What if you have a logic function and you want to figure out what the logic circuit for it would be? Let's say our logic function looks like this. F equals A and B, or A naught and B naught. How would you derive the logic circuit for that function? This particular logic function has two variables ANDed together here, and it's got two variables ANDed together here. So that means we need two AND gates. The first AND gate is going to have an A input and a B input. The second AND gate is going to have an A naught input and a B naught input. And then we're going to OR both of those AND gate functions together. So we're going to take that AND gate and put it into the OR gate. We'll take that AND gate and put it into the OR gate, and that will give us an output F. Now if our inputs are A and B, that's pretty simple for this input and that input. But here we need to create an A naught and a B naught. So we need to create a NOT gate there and another NOT gate there. This input has to be a B and this input has to be an A. So we can connect that A to that A, and we can connect this B to that B, and there we have our logic circuit. Let's make sure it really works the way we think it will. A goes into a NOT gate and comes out A naught. B comes into a NOT gate and comes out B naught. The AND gate ORs both of those together, and we get A naught and B naught. The A and B get ANDed together here to be an A and B. The A and B gets ORed with the A naught and B naught, and both of those equations are exactly the same. That makes us sure that that circuit matches our equation.